But we always call them dead days. Because you felt dead at the end of the semester. And then enjoy a final, I suppose, and then onward to your summer events, which I hope most of you are doing internships or research. So if you are not doing one of those two, you should still endeavor to make that a summer goal if you still can. Any questions or anything as we wrap stuff up? We will have some discussion of 3-day power today and look at a final. But everybody's good? Okay. So, 3 phase power. And so, what does this mean? We have 3 lines. (120° phase difference). In the voltage and current. Among the lines. So, when we looked at the last class, we started to look at some configurations, specifically the Y configuration. And we can call that VA, call that VB, call that VC, and then ground connected as a shared ground. Right down the center, and if you turn it on its side, it looks like a Y configuration. And effectively what we have is we can look up this voltage on this line, and we know by reference to ground that line has a voltage of VA, and that was called the phase voltage. In this case, VA, VB, and VC are the phase voltages. And it's the voltage of the line relative to ground. Typically, VA has 0 phase, just as a reference. Just like when we looked at source problems for single power systems, we assume that voltage source is at 0 phase. This is a common reference. We just said everything's 120 degrees out of phase. So in phasor form, VA has some amplitude, B naught, and an angle of 0 degrees. VB has an amplitude of V naught and an angle of minus 120 degrees. And VC has an amplitude of V naught, angle of 120 degrees. So there's our 120 degrees out of phase, all with the same amplitude. And so that's fairly accurate. If VA, VB, and VC are all equivalent generators, they will largely have the same amplitude. Well, what we haven't drawn here on the other side is some sort of load. And I can look at a load that looks something like this. And this winds up being a Y load. So this is ZY, ZY, and ZY. And again, we turn it on its side or whatever, and we find out it has the shape of a Y, so we have a Y configuration load. What does that mean for us? Well, we're going to look at these problems with regard to a balanced load, which is why I gave them all the same name. This is an important concept. A balanced load. Each load has the same impedance. each load branch, if you want to say, has the same impedance. So we can call this, if you want, Z1, Z2, Z3, and in this case, Z1 equals Z2 equals Z3. They're all the same. In reality, is this likely to be the case? How are these lines supplied? So previously we said this building may get VA, the JDC may get VB, the physics building may get VC or whatever. How do they choose, in some sense? How do they pick which loads go with which line? Well, a lot of it's based off experience. I mean, the goal here is to have these as close as possible. So you look at building usage, how it's going to be, how power is going to be demanded as the day runs on, and you try to set these up so they're as close as possible. And again, this comes back into the smart grid concept, where you can dynamically change these loads based on current usage, instantaneously changing loads, which is pretty amazing stuff. And it's slowly starting to happen, I suppose. But for us, balanced load, each load has the same impedance. If it's not balanced, what does that mean? Well, if it is balanced, when you look at this, this becomes a single phase system. So everything that we're doing here with three-phase, if the loads are all the same, well, there's the ground, here's the source, I trace my loop, and we can throw a little ground in there. And that little VA loop is a single loop with a VA with a phase of 0 degrees. We can do the same thing with VB. Here's the ground, here's the source, VB going through the load and then back to ground. Our VB loop is the same as the VA loop, except 120 degrees out of phase. And comparably, the VC loop, ground, trace it around, there's our closed loop. It is the same as VA and VB, except again, 120 degrees out of phase. They're all the same. Well, one of the other things we can look at here is we have an IA. And remember, these are oscillating. So I draw them pointed in a certain direction, but this is AC current, so it's oscillating back and forth. And how do we find IA? How do we find IA? The very first thing we ever talked about in this class. How would you find the current in there? Ohm's law. Ohm's law still has not gone away. IA, in this case, is VA over ZY. Ohm's law applies. So whatever impedance is associated with ZY, of course, and then the magnitude and angle of VA is known. And similarly, IB equals VB over ZY, and IC equals VC over ZY. Now recall, VA, VB, and VC are phase voltages. Just to make sure that things are confusing, IA, IB, and IC are line currents. So we have phase voltages associated with line currents. Once we know the phase voltage, we can find the line current by applying Ohm's law for this Y type of connection. And so here's a Y source to a Y load. And I would have written that above, but just to say it out. So we had a Y source to a Y load. Well, in the last class, we also started to discuss another type of three-phase configuration. And again, these are phasors. We know this is some amplitude angle 0, some amplitude angle minus 120, some amplitude angle angle plus 120, and our zy is whatever our load happens to be. So that's also some magnitude and some angle. So alternatively, we can build a configuration that looks like this. And you can still consider this is VA, that's the voltage on that line relative to ground. That's always true. This can be VB, that's the voltage on that line relative to ground, and that's VC. The voltage on that line relative to ground. But the sources are relative to the line. So in our delta configuration, delta source configuration, we have VAB, VBC, and VCA. And those are our line voltages. VAB, VBC, VCA. These are our line voltages. So VA relative to ground, VB and VC, those were our phase voltages. Voltage between the lines is the line voltage. Now, there's a relationship between VA, VB, and VC. And we'll leave off the source for a moment. So just to reiterate, remember VA was V naught, angle 0. VB was V naught, angle minus 120. And VC was V naught, angle plus 120. Well, we can go to the imaginary real plane. I think we can draw these as vectors in the imaginary real plane. There's VA, some amplitude V naught, some angle 0. There's VB. V naught angle 0, V naught angle 120, minus 120. And then there's VC. V naught angle plus 120. That's VA, that's VB, and that's VC. Well, in our configuration here, VAB is the voltage between lines A and B. In this case, this is the definition of VAB. The voltage at B minus the voltage at A, points from B to A. Well, this is some trigonometry here, that's 120. And these are bisectors, so that's 30, and that's 30. And if we go through a little bit of math, a little bit of trigonometry here, we can say VAB equals square root of 3 times V naught, angle 30. That's this vector here. So that points from here to here. It has a length, square root of 3 times our V naught, and has an angle of 30 degrees. And likewise, VCB, VBC, same amplitude, and it points from C to B. V naught, angle minus 90 degrees. And VCA points from A to C, same amplitude, V naught, angle 150 degrees. And so there's our relationships. Once we know what the amplitude and phase, if we decide to get a little bit tricky here, once we know what one of these components is, namely VA, we know what everything is. These all have the same amplitude. These all have the amplitude, same amplitude, which is square root of 3 times the phase amplitude. So in this case, V naught is the phase voltage, or VP sometimes called, and square root of 3 V naught is the line voltage, and usually VL. And so VL equals square root of 3 times VP. Or V line equals square root of 3 times V phase. It's worth writing out, just so we have more complete representation. These are the same. So that's the relationship between the two, just based on the trigonometry of the system. So again, to emphasize here, these are fair exam questions, and I've seen people mess this up a number of times, more than I would have expected. Once you're given one of these, you know all of them. They're all constrained. So there's the shift. VA has an amplitude and an angle, and everything from there on out just goes by figuring out what the amplitudes are. All our phases, same amplitude, and then the shift by 120 degrees. We can do the same thing here. There's VBC, and there's VCA. So those are our vectors. So that's the delta configuration that gives us line voltage. Now we come back to our circuit for our delta configuration. We can delta load. C delta, let's draw this delta, C delta, and Z delta. And again, this could be Z1, Z2, and Z3, but we're talking about balanced loads. And if we're talking about balanced loads, then all of these have to be the same. Now, someone asked last week, where's the ground? There is no ground. So in this case, again, we have IA, that's line current, IC, if we didn't have a balanced load. What happens here? In some sense, yeah. When we think about currents, well, these are all, if the load is balanced, these all have the same current. But if the load is not balanced, IA, IB, and IC have different magnitudes, and we can have circulating current in our system that leads to inefficiencies. And so there's no place for it to get dumped in the ground like it would in the Y configuration. So we can have circulating current, and that's a problem. So a big goal in power engineering, again, is to make sure the loads are balanced. It's very important. In a motor that's a three-phase motor, if you have circulating current, that's really problematic. You want to make sure all aspects, all loads in a three-phase motor are equal. Well, with this in mind, we have these line currents and these phase voltages, and now we know the voltage across this, VAB, in this case VBC, and then VCA, and so we have a current here. IAB, IBC, and ICA. And so that's again a circulating current oscillating back and forth in this load configuration. And so, well, how do we get this? This is Ohm's law again. So what's IAB? Well, Z delta. Ohm's law applies. This is a closed loop. In some sense, if you consider these two in parallel and ignore the transmission line effect, then voltage VAB is directly across this branch here. And likewise, IBC, BBC over Z delta, and ICA over VCA, Z delta. These, in some sense, you can call phase current. Right? That's not really the terminology, but just for symmetry. We had phase voltage and line current. Now we have line voltage and phase current, though the more common terminology is called branch currents. I include phase just for some completeness, for some symmetry. And so we have, again, the phase goes with line current. And now we have the line goes with I phase, or branch, is really what's used. Yeah?
What is all Z mean?
Delta. Z delta. For the delta configuration. So it's the Greek delta. Z triangle, if you will. Z delta. Well, so in some sense, we can generate these phase voltages with either a delta or a Y configuration. We saw the relationship to generate the same voltage on a line. We have these relationships between. These are equivalent. So these are equivalent source circuits. So I didn't emphasize that enough, but to emphasize, when we build these configurations, and I labeled this voltage on this line as VA relative to ground, we can do that with either a Y configuration that we did initially, or with a delta configuration with these source values. And if we go through a bit of math here, we can wind up and discover that I line equals square root of 3 I branch. These are amplitudes. And that comes out of the same trigonometry. Now, we have this delta configuration and this Y configuration. Here's our Y. Where did my delta go? There's my delta and my Y. If I'm generating the same, if I'm saying these are equivalent circuits that we can represent in two different ways, what must be true? Well, the voltage VA, VB, and VC, all the same, of course, IA, IB, IC, has to be consistent. But for this to represent equivalent systems, really, what do I care about? Ultimately, it all comes down to one thing, and what is that? Power. We really care about power. So if we look at these systems, well, in this case, what's our power? We can look at power at just one of the branches. And our power power expressions haven't changed. You can say S equals V I conjugate. That's the same thing we've done all along. And so if we're looking at our Y configuration, well, equals V phase I line conjugate. And so that has to be equivalent. Or alternatively, we can write this as V phase, and this is a put a little note in the corner, RMS values. If you want, we can put a little 1/2 in front, call them amplitudes. Z, Y, conjugate. Or alternatively, I line squared times ZY. This is complex power, depends on what ZY is. And so the same thing we've done before, nothing's changed. But if they are equivalent, alternatively we can say V equals I conjugate, which has to be V line times I branch conjugate. And these are equal if circuits are equivalent, which they have to be. And so our whole theory here, our whole model says that we can build equivalent circuits, achieve the same power. And again, we can go through the same set of three expressions. Delta conjugate, and then I phase squared times Z delta. And again, we get complex power. Well, all that said, we know the relationship between all these sets, but if we look at these two, well, we have our V phase and our V line relationships. So in this case, if we just look at this guy and look at this guy. And so, well, V phase squared over ZY conjugate has to be equal to V line squared over Z delta conjugate. And then parentheses again, I'll write if equivalent, which is our goal. So when are these equivalent? When can we represent one as a Y or a delta in either case? We could write this as V naught squared. We used that amplitude before. It's an arbitrary assignment. Some voltage. And that's still ZY conjugate. And what's the line voltage relative to the phase voltage? Well, it's square root of 3 V naught squared. Bless you. Z delta conjugate. And a little bit of rearranging here. This cancels. We lose our V naught on either side. And what are we left with? Z delta equals ZY times 3. Or to write it a little bit more reasonably, 3ZY. Equivalent representation between configurations. So you can walk back and forth between a delta or a Y configuration on the load. by using this relationship, and that maintains power. And so we can connect then a Y load with a delta source. And if we want to analyze that, we convert one, either the delta source to a Y source, or Y load to a delta source. So either way is viable. Certainly here, if we want to analyze power, you have phase voltage, and that very quickly gives you information on power of the Y load comparably with the delta configuration. But if we mix things up, and we do this, VA, VD, DC, how do we analyze this circuit? Oops, nothing there. So we have a Y source and a delta load. How would you go about analyzing this? And what would you do? You didn't quite catch that. But how would you do it quickly? I mean, there you'd have to do some trigonometry. Well, I would convert to delta, or convert to Y. Is that what you're trying to say? So either way, and those are analyzed quickly. If we convert our delta source to a Y, we can get power in each branch by just doing VA over ZY. So this is our Z delta, Z delta, Z delta, or alternatively, convert our Y sources to the delta source with the square root of 3. So either one better give us the same power. The analysis better be equivalent. And so you can go either way. Is it clear? Anybody have any questions on this? Ultimately, this is three-phase. In my experience, it's not necessarily very intuitive, but the thing to recognize here is if we're looking at a balanced load, ignore the three-phase aspect of it. I mean, ultimately, if we're talking about balanced loads, which is all we're talking about in this class, and I think all you'll actually talk about in energy systems as well, if we're looking at a balanced load, it's the same problem that we've done all along. It winds up just being three individual single-phase problems. If you want to study imbalanced loads, then go to graduate school. Lots of job opportunities historically in power engineering. Anybody know where the real big money in power engineering is? Historically true, probably still a little bit true. No, teaching's never the big money. Unless you get lucky enough to sell a book or something that everybody uses, but I think even those days are gone. Everybody online. No. Certainly, if you do something unique and you patent it, you can make big money that way. But big money's on Wall Street. And that's a true story. So trading power algorithms, and consulting with developing code for Wall Street. A lot of power engineers have gone to the dark side when they've seen those $250,000 salaries. and gone down to Wall Street and helped the brokerage firms. And that's probably still available. So something to think about. Usually you need a master's, if not a PhD. It's usually fairly math intensive, but it is true. So a lot of opportunities in power trading. I don't know what the markets are, but still being done to this day, actually going faster and faster as real-time trading was taking place. Historically, it was maybe by the week or the month. Now it's getting down to by the hour, by the minute. So you make lots of good money that way and get to live in New York with gold doors. So we'll do our last class problem, then we'll look at one other one.
My friend did. I don't know if he uploaded it yet.
My artistic ability has not improved. That's a delta load with a resistor and a capacitor. So there's our effective delta load. We have a resistor and a capacitor in parallel. And if you do the math, it winds up being 250 minus J250. And we have some line VA, VB, VC. And again, this is a delta load, but VA was given. Only one more day of doing that. 1,000 angle 0. And if you still have the handout from the last class, it looks something like this. We're asked to fill in the various VAs, VB, VAB, etc., etc. Well, we're given VA. So very, very quickly we can do the whole phase voltage line. This is 1,000, angle 0. That's 1,000, angle minus 120. And that's 1,000 angle plus 120. So fairly straightforward. And then what else can we do very, very quickly? The line voltage. That was the square root of 3 relationship. So this winds up being square root of 3, 1,000, angle minus 30, plus 30. 1,000 square root of 3, angle minus 90. I realize that's hard to read. If you're having reading issues, let me know. Angle 150. So that's VA, VB, VC, and VAB, VBC, VCB. Okay. So we have our phase voltages and our line voltage. Now, having done the voltages, and that's again fairly straightforward bookkeeping, once we're given one of our phase or line voltages, we can extract all the others fairly quickly. What would be the next thing we would determine? Well, what's the configuration of our load? I just drew it a second ago. What was it? Delta. So which one of these do we want to use to find the current? We want to use the line voltage because that gives us the branch current. The line voltage and the branch current go together in the delta configuration on the load. And likewise, the phase voltage and the line current go together in a Y configuration on a load. So we have a delta load, line voltage, and branch current relationship. In other words, V line equals Z delta times I branch. Ohm's law. Or since we're given V line, I branch equals V line over Z delta. And so, well, this was 250. You can write this out as 250 square root of 2, angle minus 45. We can do a little bit of math there. VAV for square root of 3, 1000, angle 0, or angle 30 degrees, over 250 square root of 2, angle minus 45, winds up being 4 square root of 3 over 2. That's probably really hard to read, but hopefully infer it. So 1000 over 250 is 4, there's the 4, and then square root of 3 over square root of 2, and angle 75. That's in the denominator, so 1 over minus 45 is 30 degrees plus 45. And likewise, after that, similar repetition, square root of 3 over 2, angle 45, minus 45. What's wrong? Square root of 3 over 2, angle 195. Or if you prefer, angle minus 165. Or 150. 165. And so now that we know the branch current, or what phase current there, but now that we know the branch current, what can we do? Well, we can get the line current by just using our square root of 3 relationship. Recall I line equals square root of 3 times I phase. And so we have 12 over square root of 2. And then we have a phase shift of 30 degrees. Just based on the geometry that we did before. 12 over square root of 2, phase shift 30 degrees. 12 over square root of 2, phase shift 30 degrees. And we're done. What's a quick check? Well, we can check power between these two and these two. And if you check power, they are consistent. And that's it. Well, I do have one more thing to talk about. Always glad about stuff like that. Any question on it? Very straightforward. Just becomes bookkeeping, keeping track of Ohm's law, getting it in the circuit, equivalent circuit that gives us the easiest extraction. Everybody okay? One parting thought as we look at three-phase power. Total power. We need three-phase total. And for simplicity's sake, let's consider resistive loads. And so we can look at the Y configuration. Let's say VA equals V naught angle 0, and IA equals I naught angle 0. And then everything after that is just some sort of shift. It's a resistive load, so these are in phase, right? Something to recognize, something to be familiar with. Resistive load means VA and IA have to have the same phase. Then if we look at power in line A, well, power in line A, and I should be a little careful here, let's use my S. SA is VA times IA conjugate. And let's go back to representing this as a sinusoidal signal, or cosine as the case may be. B naught cosine omega t, I naught cosine omega t. Right? Then we can write this out as 3 B naught. I don't know where the 3 came from. Thinking way, way ahead. Cosine squared omega t, which is B naught I naught 1 plus cosine 2 omega t over 2. Right? No problem. Trigonometry is always fun. Well, let's consider line B. Well, let's do the same thing. SB in this case, well, the amplitude of B naught, or the phase of B naught, phase of B is minus 120, so we get B naught cosine omega t minus 120. I naught, and since again it's resistive load, cosine omega t minus 120. So again, the same geometry. Then we can skip some steps here. We're going to wind up with V naught, I naught, 1 over 2 cosine. I wanted to skip steps and I'm not doing it. V naught, I naught, 1 plus cosine 2 omega t minus 240 all over 2. Let's just take advantage of our trigonometry. Well, let's apply a little bit more trigonometry because it is fun. And so we wind up with plus cosine 240, that's angle, cosine 2 omega t, plus sine 240, sine 2 omega t. Right? I think I got my trigonometric identity correct. All over 2, of course. So I just applied some trigonometry, cosine of 2 arguments. Yeah.
The second argument needs the B naught I naught.
Yeah. Out front, sure. Here. Well, if I evaluate what cosine 240 is, it's all the way around, so we wind up with B naught I naught 2, plus there's our B naught I naught, of course, and that should be minus 1/2 cosine 2 omega t, in this case, minus 1/2 sine 2 omega t. And again, all over 2. Well, and I'm trying to keep the other one up here. Maybe we can just write this as one more step. B naught I naught over 2 plus B naught I naught cosine 2 omega t over 2. So there's our SA. And I'm going to totally shortcut our SC. Sorry, I'm writing down trigonometry. But we're going to wind up with something that looks like B naught I naught over 2 plus B naught I naught plus 1/2 cosine 2 omega t plus 1/2 sine 2 omega t all over 2. And to get things close together, let's write SA again. I'm just in the minus 1. SA equals V naught I naught 2 plus V naught I naught cosine 2 omega t over 2. Well, if I look at all these guys, if I add SA plus SB plus SC together, what happens to my two sine terms? Simple addition. What happens to my two sine terms? What happens to my cosine terms? And lo and behold, there was the 3 I put down initially. And I was thinking way far ahead. Or if we write this out in our familiar form, VRMS, RMS. So lo and behold, what can we say about the instantaneous power, which is what we just looked at? This is our instantaneous power. And we looked at that when we first started talking about AC, DC sinusoidal power. Our instantaneous power is what? What type of number is this? What type of function is it, I should say? It's a constant. 3-phase power with a balanced load. Produces constant instantaneous power. All that trigonometry, discover that. As a function of time, we have 3 VRMS, IRMS. Constant instantaneous power. As opposed when we were looking at single phase, what did our single phase instantaneous power look like? Well, it was oscillating something along the lines of this. Which is why we went to RMS to begin with and calculated average power. Why is constant instantaneous power better? Why is it better? I brought it up once before. Why would we care about this? Why do we care about this? This is beyond the scope of the class, but if we're going to bring up this aspect that it's constant, we may as well put it in context. Why does it matter? Well, to really go beyond the scope of the class, if you think about an induction type motor, it looks something like this in a simple sense. You have a bunch of coils here with AC power oscillating back and forth, producing a magnetic field, and you have a bar of something like iron. And so if I have a magnetic field that's doing something like this, what does that iron want to do? And this is something everybody knows because everybody's played with a compass. What does iron want to do? Wants to line up with the magnetic field. But this needs to keep spinning. If I have this as a constant, what happens? Well, it goes and lines up and eventually it just settles there. So that's the whole point of AC is you magnetize this, the iron lines up, but as it gets closer, the AC field drops to 0, the magnetic field drops to 0, it flies past, you reverse the magnetization, and it keeps going around in a circle, and thus we have motion. Well, if you think about this, you're constantly turning the magnet on and off. So what does that do to this bar? So you're constantly changing the power. It is beyond the scope. essentially, what are you doing here? Yeah, I mean, those are on the right thought. You're magnetizing the bar, then demagnetizing the bar, you're magnetizing the bar, then demagnetizing the bar. And what is that doing? It's putting stresses on the bar. Well, arguably, three-phase can put less stress on systems. This produces vibrations in our system, 60 hertz, 120 hertz, higher order harmonics. If things are done well, and there are still vibrations because it's not perfect, but if things are done well, three-phase systems have less vibrations, they're less stressful, and more constant power. You're not going to have any slip, presumably. You don't have to worry about things rotating backwards. So something for you to ponder about as you're not studying for other finals. That's not on the final. You don't have to worry about how motors work. Who votes A? Minus 12. It's on the same token. What about E? B? B. Should have given polarities in there as well. What about C? Who votes C? Who doesn't vote C?
I can't really see.
Can't see? Oh, the light. These lights? Actually, I think you can turn off the front. You want to try to play with the lights for a moment? So,
Everything but that.
yeah. Milk and cookies next week. Now I'm really tired. KCL applies if we do KCL at the node. Well, if we do KCL here, what's the current entering? What's the current leading to the right? What's the current through R1? So what's the voltage across R1? There you go. Trying to maximize power. How do we maximize power? What must be true in a system, an AC system, for power to be maximized to the load? In that case, RS equals RL, or effective RS equals RL. So what does N have to be in this case? Square root of 10. Does everybody agree with that? Anybody not sure where that came from? There was a mumbling response there. Is anybody not sure? So no matter what, whatever type, oh, that looks weird. Oh, that's worse. You need the lights again for a second. Oh, I see. I don't know why this light never turns back on. Really not going to work, is it? Can you get the lights for a second? Thanks. So no matter what our system is, ZL, if we consider this R Thevenin and V Thevenin, which we always can, we can always, let's call it Z Thevenin. We can always ultimately get our circuit in this form. Remember, off to the left, we can have all sorts of crap. We can have inductors, capacitors, resistors. As long as our load is unchanged, we can do equivalent circuits and find a V Thevenin and a Z Thevenin. And in this case, power is maximized to ZL. When ZL equals Z Thevenin conjugate. I know we called it ZS before, but it's the equivalent. I mean, it can always break it down in this form. So when these are complex conjugates, power is matched by, one of the things that we see when it's complex conjugates is the effect of impedance seen by the source is purely real, which means we're producing real power. In the case of the transformer circuit that we just had up, we had what, 100 or something? One K and one N. And so, well, if we do Thevenin equivalence here, what do we wind up with? Well, Thevenin equivalence, we can say, is comparable to referring the primary to the secondary. Because that leaves our load unchanged, which is the whole point of Thevenin equivalence. So essentially we would open circuit that load, find the open circuit, and then short circuit to find Norton, or use our Thevenin method, whatever you want. So referring the primary to secondary, this was some being odd. What do we wind up with? N being odd. N squared 100 and 1K. Well, again, Z Thevenin equals Z load, which only happens when N squared equals 10 or N equals square root of 10. So that maximizes power to the load. The transformer is just another aspect of that circuit, but ultimately we reduce it to something that's a single source impedance, and a load impedance. And we look at that circuit. On the same token, we apply the same reasonings for the second problem that has a capacitive and resistive source impedance and a load impedance that's going to be what? You don't have to be specific, but in general, what would the load impedance be? An inductor and a resistor. The resistor we can do quickly by observation. It is again going to be 300 ohms. The inductor, well, omega L has to be equal to 1 over omega C. Frequency was given at 159, which quickly gives us 1 kiloradians per second. And so then you can solve that up. Some questions about real transformers. Design coupling coefficient is 1. The desired coupling coefficient is 1. Is that true? Yeah, of course. I mean, that's your goal. You want strongly coupled inductors. Otherwise, it's not really a transformer. The winding ratio is always 1 to 1. Well, hopefully we agree that's not true because we actually looked. The power produced in the primary goes to 0. In this particular case, talking about RS and RL, as frequency goes to 0. Is that true? So if this becomes a DC system, as frequency goes to 0, effectively frequency going to 0 does what to our T model? Well, our T model is 3 inductors, and as frequency goes to 0, what happens? They short. Does the power produced in the primary go to 0 though? No. So there's an RS in there, we can drive current. The power consumed in the secondary goes to 0 as frequency goes to 0. Is that true? Yeah. It goes to 0. We're short-circuiting the load effectively. And if you did that circuit in P-Spice, you would have seen that in the AC suite. Frequency operation is dependent on the inductance of the 2 windings in a real transformer. True or false? True. So, it's dependent on L1 and L2, which affects M. And so, remember we talked about that. In the real transformer, or in the op-amp ideal transformer, or not op-amp, in the ideal transformer in P-Spice, well, effectively, if it's an ideal transformer, what must be true about the inductances? if it's operating in all frequency ranges, all AC ranges, let's not talk about DC. Effectively, what must be true about L1 and L2 for it to be infinite frequency range? L1 and L2 are infinite. So the only way we can get infinite frequency range is to have infinite inductance. And so our inductors limit our operating range for our transformers. So, about transformer step down, winding ratio n to 1. So step down. The secondary is short circuited. What's V1? V1 and V2 are trivial. V1 and V2 are 0. Comes out of our ideal transformer relationships. V1 and V2 must be 0. What's I1? Oscar should be trivial now. Not 0. If V1 is 0, KVL applies. What's I1? Can't be V source. Vs over R1. Thank you. So I1 is Vs over R1. If it's a step down transformer, n to 1, is I2 larger than I1 or smaller? It is larger. It's a step up transformer, it's smaller. Those are our ideal transformer characteristics. It's my last piece of paper, so we can't have any more discussion. If this is 1 to n, call that V1, call that V2, call that I1, call that I2. Our ideal transformer relationships, n times V1, there's our ego. So if n is less than 1, like it was in this problem, that was n to 1 instead of 1 to n. If we look at the, should have left a little bit more room here. This is step up. If we have step down, we could arguably write it as n to 1. And in this case, well, V2 is V1 over n. And I2 is NI1. Alternatively, you could just say n is some number between 0 and infinity, some positive value. But in this case, writing it like this is this relationship. Well, we just went over this. Is the above circuit, is it a delta circuit or a Y circuit? It's all Y. So VA is given. Find IB in phasor form. I should say phasor form, phase form. I don't know why it says phase form, but. So what's IB? Using the same thing we've done before. What's VB in phasor form? 500 angle minus 120. VB is angle minus 120 using our convention. And so, well, VB is 500 angle minus 120, and this is a Y-type connection. Ultimately, we can treat it as single phase lines and apply Ohm's law. Our resistive load is 75 ohms with a Y-type load. We know the phase voltage is 500 angle minus 120, so the line current 500 angle minus 120 over 75, which is some number, 6 and change or something like that. In that case, the branch current in phasor form can be gotten how? Well, that's the square root of 3 relationship and the angle 30 degrees. And that was it for short questions in this exam. So mesh node analysis, I assume that this should be, yeah.
Going quickly back to the delta, If VA was given with an offset phase, would every other?
Everything shifts by that, and I did that once and I realized it was stupid. So I won't do it again. Because you can define VA as zero phase. You can always define one of them as a reference phase. Use VA, it's the convention. So I did that once for no reason, and I realized that there was no reason.
Can you show the ideal transformer when you have the overhead?
This one? Just these expressions? I mean, this applies if you include values where n is less than 1. So this is always valid. But you can write things like this as well. So here the kind of the assumption was n some value larger than 1, but it doesn't have to be. So everything here should be old hat. We have some circuit analysis, mesh analysis, straight up DC problem. I don't remember how people did on it, but dependent source problem. Again, nothing as an art evident problem, so it's been a while, things to review. Transient problems, again, go over to Unit 2, Unit 3. No particular surprises in the exam, maybe things written a different way, but Bodie plots, everything, we're very familiar with that, haven't done that recently. And then, again, a whole problem on uniform material, so we have, inductance, so we have transformer relationships. Can't remember what the problem was. If I recall, everything canceled out nicely, though I don't remember if that was the case or not. Was the goal. So, if you had a problem like this on the whole, anybody need to particularly see this? Again, something similar or familiar. We have a T-model mutual inductance. I know a couple people ask me questions on the T-model. Is everybody comfortable with drawing the circuit? I mean, this is kind of important. I had a number of people ask me, if their circuits were right, and we had to look at it a little bit more closely. I mean, the whole goal here is kind of block this out. Highlighter here. No, that's not going to work. You block out that T-model section, so if we put a little rectangle around these two inductors, everything outside that rectangle has to stay the same. So you can't change that circuit. So you don't change this voltage source, you don't change this resistor, you don't change this transformer or capacitor or anything like that. So when we do the T model here with this circuit, all we're doing is we're cutting this out, we're putting a T in here. So when we're drawing across and then down, and then connecting up the nodes. You don't change anything else in the circuit, that's important. So there were a number of people who redrew the circuit. All you're doing is cutting this part out and replacing it with equivalent inductance. And by observation, we should say, some of this problem fairly straightforward. So M was given, L1 minus M is 2. M is 2, and then L2 minus M is 0. So that certainly makes the problem more easy to analyze. And now we coupled it with the real transformer as well. Everybody okay with this problem? Anybody need to see the circuit drawn out? Anybody want to see the circuit drawn out? And then power. And again, not so dissimilar to what you saw in the homework. Won't guarantee you're going to get the same type of problem, but something to complete, fill out the same chart. It's accounting. This is accounting for engineers. Power consumed has to be equal to power produced. And unlike accountants in industry, we actually have to balance. We can't cheat. We don't go to jail. If we screw up, people get hurt. So we have to be real. So there's more exams, but really all I wanted to do was go over the short answer questions again and be somewhat of a discriminator. Yeah.
Usually the time frame that's given for this exam.
Do people finish early? Is that your question?
No. Is it similar to like, really like time constraints? You're not gonna finish in time?
People tend not to finish early. A couple of times, once it was because I had a really bad
Expect to
problem.
finish early? Do you
It
have
happened
to?
one semester, a really bad problem on the final. Only happened once, but other times, just kind of a lot to do. Yeah, I don't remember big chunks of people finishing early. There's always a few, including those who give up.
Oh, good.
I assume that's it.